Hi, I'm going to do some differential equations problems here. If you want to really be like a cool math nerd, is that oxymoronic? If you want to be a cool math nerd, then differential equations, sometimes they're called diff EQs, diff EQs, differential equations. They're definitely not difficult equations. It doesn't stand for that. They're pretty easy. Let's see. Let's do some. 15 through 31 all, except for 23 and 25. Your math teacher made you do all of these, not the odds. That's kind of jerk move. Oh well. Okay, so I guess they must be easy. So 15, we've got dy dx is equal to y over x. So we need to separate the variables. So the y goes on this side, 1 over y dy. The x's stay on this side, so that's 1 over x dx. And then I take antiderivatives. Antiderivative of 1 over y is natural log y is equal to natural log x plus c. If you want to solve this for y, then you have to exponentiate. That means you do e to the this and e to the that. So e to the natural log y, of course, is y. And then e to the natural log x plus c is, the c can come down to the front. That's, oops, sorry, for my y equals c, and then e to the natural log x is just x. If you're looking at that being like, and thinking like, wait, what just happened here? That's like y equals cx. That's like a direct variation. That's like y equals slope times x. So what's that about? Well, if y is rise and x is run, then if the slope is equal to y over x, then you are on a line that goes through the origin. So sure enough, that's the general form for all equations for lines that go through the origin. Ooh, I was going to write down 17, but we have to do all of them. Bummer. I'm going to spare you the writing down of the problem part, and I'm going to go straight to separating because I know how to do algebra, and so do you. So I'm going to divide that 1 plus y squared over to the other side. I'm going to leave the 2x here, like that. And then I'm going to find antiderivatives. Antiderivative of that is tangent inverse of y equals antiderivative of that is x squared plus c, put my constant over here. And then if you want to solve for y, which is always desirable if you can do it, then to get out of tangent inverse, you have to just take the tangent of both sides. And it is super important that that c is inside here and not tangent of x squared plus c. You need to think about that, but those two things are not the same expression, for sure. Number 17. All right, let's see. To separate here, need to leave the y's over here. And then on the other side, I've got negative x over the square root of 1 plus x squared dx. Antiderivative of this is just natural log 1 plus y. And then here I'd have to do a u substitution where u is equal to 1 plus x squared, so du is equal to 2x dx. So I need a 2 in here and a 1/2. Actually, I think a negative 2 in there, so that'll take that sign out of play. Rather move that sign to the outside, however you want to think about that. So where does that leave me? That's the rewrite of this part now is negative 1/2 the square root of u to the negative 1/2 du, which is negative 1/2, bump that up to 1/2, and divide by the new exponent, which is 1/2, so that would just turn this into a 1. So negative u to the 1/2 plus c over here, and u is this. So that's the square root of 1 plus x squared plus c after I do that u substitution. And then if we want to exponentiate, that would give me 1 plus y is equal to e to the square root of 1 plus x squared plus c up here, but that can move down because that would be the same as like e to the c, and e to the c is just some other constant here. So that's a common move. When you have the plus c, we're going to see that a lot because of the types of functions, the types of differential equations we're going to get good at solving. When you have the plus c up here in that exponent, that can come down as a new constant. I just made a c1 there just to keep it straight from this. So finally, y is equal to this c1 times e to the square root of 1 plus x squared minus 1. Let's check that, make sure that all is okay. I got a negative sign there. The book, they have a negative sign, so did I mess up something with my u substitution, perhaps, when I was like juggling the signs in here, or here? Maybe I did. Let's see, so I needed a negative 2 on the inside, which means I needed a negative 1/2 on the outside. Oh, there's a negative sign there, and I just ditched that. So, there. Fixed. All right, number 18. Let's see, when we separate this, it looks like we're going to have, and there's no choice about which side you have to go to with things. So you can't have like 1 over dy. The dy has to stay over here, and the dx has to stay over here. So x cubed over 1 plus x to the 4th. So that looks like a u substitution, because I got an x to the 4th here and an x cubed there. And I've done calculus before. So I don't know why I wrote that down. I have done calculus before, really. So I need 4x cubed there, so that means I need a 1/4 on the outside. And now my antiderivatives. Maybe I'm going to rewrite this just with the u. So that would be 1/4 integral 1 over u du. So that's going to give me y squared over 2 is equal to 1/4 natural log u plus c. The u is 1 plus x to the 4th plus c. You could multiply the 2 over to the other side. I guess you could solve it for y. You could take the square root and put a plus or minus in front. I don't really see a great advantage in doing that. What does the book do? Yeah, they actually do the square root plus or minus thing. But my feeling is, my sensibility is, if it's not a function, like if you have a y squared in there, then don't try to solve for y. You can leave the y squared in there. So like similarly, I think it's probably better to have, like this is the equation for the unit circle, for example, which of course is not a function. I think that's better than solving for y and forcing it into this with the plus or minus, because that's more familiar to us. It's like, oh yeah, that's the unit circle. And when we see that, we're like, what's that? So that's my feeling about it. I would probably just leave it like that. Number 19. I have that y prime means dy dx, so I will rewrite it like that, or think about it like that. So 2y, so I need to divide that y over to the other side. That's going to give me 2 over y plus 2y. You see where I'm getting that there? I'm dividing through the 2 plus 2y squared. I'm dividing that all by y, term by term. So it's that dy is equal to e to the x dx. Where'd the dx come from? Because I turned the y prime that was on the left into dy dx. That's where that came from. Antiderivative, let's see, so this is 2 natural log y plus y squared over 2, sorry, just y squared, not over 2, is equal to e to the x plus c. Want to solve that for y? Good luck with that. You can't do it. So we are just going to leave it like that. Number 20. Y prime, which is the same as dy dx, equals negative xy. So that means my dy on this side, I'm going to have 1 over y. I'll always leave negative signs and constants over here with the x's. So antiderivatives, I forgot to do that in this problem above. So that negative x squared over 2 plus c, this one I can exponentiate, so that would give me y is equal to e to the negative x squared over 2 plus c, but that's that same thing. That's really like times e to the c, and that's just like another constant. It almost feels like that, like a logarithm rule where we're bringing down the exponent, and it's kind of sort of related to that, but it's not the same as c, right? All right, just give that a quick check. That's all good. All right. If I can just separate this from, oh my goodness. Why is this so hard? There we go. Ah, those papers were stuck together. Broke a sweat there. Number 21. We have some crazy stuff here. Can we do... Okay, so this one, the first thing we need to do is have this written out in such a way that we can actually separate things by multiplication and division. So I'm going to get the thing with the derivative on one side and the other thing on the other side, like this. That is what we're going to do. And then I'm going to do, so what's on the side with the dy, I need to move this over to that side. Now that's, of course, this is really 1 over e to the y. So when I move that to the other side, it just turns into e to the y. So that's nice. And then on the other side, the dx, I have sine x over cosine squared x. So that is, after a little bit of trig identity snooping, and also like anticipating the kind of things that we know and what we're able to do, maybe that could also inspire you to see that sine x over cosine squared x is actually the same as the sine over cosine is tangent, and then the 1 over the other cosine is secant. And that's good news, because I know that the antiderivative of e to the y is that, and then the antiderivative of secant tangent is secant. And then you want to solve for y? Sure, do the natural log of both sides. That's how you do that. Number 22. Same thing like we did last time. The first thing I need to do is get... I can't have this addition subtraction stuff. I really need to separate things only by multiplication and division. So I'm going to do that first. And then I got the 1 plus y squared. That's going to have to come over here with the dy. And then 1 plus x is going to stay here with the dx. Okay, so when I do my antiderivatives, that is tangent inverse y is equal to x plus x squared over 2 plus c. And then if I take the tangent of both sides to undo that, that gives me y is equal to tangent of x plus x squared over 2 plus c. Same thing, gotta get this over here so I can better separate. Okay, so let's see, that's going to be 1 over y squared minus y is equal to 1 over sine x. Oh, is this one of the ones I'm supposed to skip? It is. I was just looking at that, going like, where is this going to go? This isn't things that we know how to do. So never mind that one. 24. Is it doable? Yeah, but this you have to do partial fractions, and then that's a trig thing that in a section that we skipped in Chapter 8. So that's why we're skipping it. How about this one? Can we do this? Moving things around, dy dx, secant x is equal to y. That's just moving things around with algebra. And then more moving things around with algebra. Divide the y over and divide the secant x over, which turns it into cosine x. So antiderivatives, that's natural log y is equal to sine x dx. Just kidding, sine x plus c is what I meant to say. And then if I exponentiate, I get y is equal to e to the sine x plus c, but that can come to the front as a new c. That was 24. Looks good. 25. Oh, that's another one I'm supposed to skip, isn't it? So same thing, that involves a different technique that they go over in this chapter that we're not going to do. We're only going to do separation, not the other thing. You can go check that out if you want. Read about it in the section. But it's not for us. So in each part, for number 26, find the solution of the differential equation that satisfies the initial condition. So vocab-wise, what we're doing now, everything we did so far, those are general solutions. They have the plus c in it. They're like whole families of solutions, depending on what c you pick. Now in 26, in problems like this, we have a point, which means we're going to be able to solve for the c, and therefore we are finding what we'll call a particular solution. Our book doesn't really emphasize that particular solution vocabulary, but that's the way that we would like to talk about it. So what do we have? dy dx is equal to xy. So that's 1 over y dy dx. 1 over y dy, rather, is equal to x dx. And natural log y equals x squared over 2 plus c. E to that, it just gives me y is equal to e to the x squared over 2 plus c, but that can come down because that's just like e to the c, so it's just another constant. All right, so there's my general solution, and then I want the particular one for a, the point 0, 1. So if y is 1, when x is 0, then that constant is just 1, and my particular solution is y equals e to the x squared over 2. For b, y of 0 is 1/2, so 1/2 is equal to C1 times e to the 0, so the C1 is just 1/2. So there's my two particular solutions that go through those two given points. Number 27. Solve the initial value problem by any method. Well, for us, that means that we are going to do separation, because that is our method. These are initial value problems, which means we're finding particular solutions. We are being given a point. So that's the idea. I'm going to go ahead and rewrite this one, get all the x's and y's. So that's 2xy is equal to 2x. And then I could factor out that 2x. So that's important for us to be able to have x's times something with y's, to have those kind of separated out, because then we can do what we need to do, separate the variables. So natural log of y plus 1 equal to x squared. I was going to write over 2, but that's not right. So then e to the, that gives me y plus 1 is equal to e to the, I can bring down my constant again. You get the hang of this, right? So y is equal to c1 e to the x squared minus 1. And then I have to find the particular solution that goes through the point 0, 3. So the point that's going to be a 3 there is equal to c1 times e to the 0 is just 1 minus 1. So c1 is 4. So that means we're going to have y equals 4e to the x squared minus 1. That's my particular solution. Particular. And what are we on? 28? What are we going up to? 31. We're getting there. 4 more. 28. So, this one has t's in it, but that doesn't really change anything at all. Of course, from a physics, dy dt, that makes us think of, that's like the rate of change of the vertical position of something. Probably should make you think of that. And we have the initial condition 0, 1. So we'll use that in a minute. Let's do this first. So separating, dy over 2 minus y is equal to, and then the dt comes up here and there's nothing. We divided that whole thing over. This is kind of a common situation here, where this is some kind of function of y over here, and we divide the entire thing down to here, and then up here is just the dx or dt in this case. Now this is also common that we have the 2 minus y. You could write out a little u substitution, but we know this is just going to be natural log because that's y to the first power. But don't forget, because there's a negative on here, we have to divide by that constant -1. This is one that the College Board quite likes, this little thing with the negative sign in here, to see if you get this. And you lose a couple of points. Out of your 9 free response points, you're probably going to lose 2 if you mess up that negative sign. You don't want to do that. So now this has to, before you can exponentiate, you can't do the e to the natural log thing and have them cancel out unless there's nothing in between here. There cannot be any intervening stuff. So this minus sign needs to go over to the other side. And of course the C1, you can multiply that by a negative sign. It's just a constant that I haven't solved for yet, so then you could call that like plus C1, whatever. It's just like that would be the opposite of this. And now I can exponentiate. 2 minus y is equal to e to the minus t, and then the plus c1, that could just come down here as another constant. And then I want to solve this for y, so y is equal to 2 minus some constant there. I'm not going to be super fussy about how you keep track of your constants here, but you just have to have it in the right place when you get to here so that you can use your initial condition, which is 0, 1. So when y is 1, 2 minus c2, and then e to the 0 is just 1 again, so it looks like c is going to be equal to 1. So y equals 2 minus, that's just 1. Looks like we have that. Let's check that, make sure that we're good. Yep. Number 29. All right, so they wrote y prime and said dy dx, but I know that means the same thing. So separating out, I'm going to have 2y plus cosine y dy is equal to 3x squared dx. Okay, antiderivatives, it's y squared, antiderivative of cosine is sine, y equals x cubed plus c. And nothing you can do here to try to solve for y because there's a polynomial and trig happening to y, so no luck there. So what's my initial condition? It's 0, comma pi. And so let's see, if I plug in pi squared plus the sine of pi is 0 equals x squared is 0 plus c. So it looks like c is equal to pi squared. So there you go. Y squared plus sine of y is equal to x cubed plus pi squared. Let's check that. Groovy. That's the correct answer. Number 30 is, I think I need a step of rewriting here. So dy dx in place of the y prime, and then I'm going to add over to the other side 2e to the y plus xe to the y. So those two terms have an e to the y in common, which could be factored out. And now I can separate. So moving that over to here, that would be 1 over e to the y, but that's the same as e to the negative y. We saw that come up somewhere else in this problem set. Okay, what's the antiderivative of e to the negative y? Antiderivative of e to the whatever is e to the whatever, but since this is a linear, just a linear factor of y, I just need to divide by that constant. All right, so don't forget that negative sign. That's going to cost you. Antiderivative of 2 is 2x. Antiderivative of x is x squared over 2 plus c. Negative sign, this negative sign, coming over here, and that c can take it. Can just be a new constant if I multiply it by -1. And then if I want to try to solve for y, I think I can do that here. Natural log of both sides. That gives me -y is equal to the natural log of -2x minus x squared over 2 plus c1. And then if I want to get y equals, not negative y equals, I can move the negative sign to the other side. So what's my initial condition? It's 0, 0. So if I plug in 0 for y, it's equal to negative natural log of 0 minus 0 plus c. So let's see, what's the C1? The C1, if you want to have the natural log of something and have that be 0, that's got to be, the natural log of 1 is 0. So C1 has to equal 1. And there you go. So our final answer is y equals negative natural log of negative 2x minus x squared over 2 plus 1. And let's just check that. 1 minus 2 minus 1. Yep. That's it. 31. So let's see. Ready to separate here? I think so. So 2y minus 2 dy equals 2t plus 1 dt. Antiderivatives. It's going to be y squared minus 2y equals t squared plus t plus c. And can't solve that for y, so not going to try. And let's see, my initial condition here is 0, negative 1. So when y is negative 1, I get 1 plus 2 is equal to 0 plus 0 plus c. So it looks like c is 3. So y squared minus 2y is equal to t squared plus t plus 3. All right.